Okay.
1 minute.
How long is this?
Start.
I think there is some latency.
Start. Start.
Yeah, it started. Nobody's asking anything though. Hello, somebody's saying hi. I don't know what. Those related questions, I think the questions that I had put for.
Good.
Yes, Satish. Yeah, no problem.
Hello.
So, I will just introduce this session and then I think we can go on. We are live now?
Start.
It's already started.
Start.
Okay. Hello guys, good evening and apologies for the delay. There was a meeting that we had among the TAs to discuss about the course, how things are going in the course and what we need to do to improve some of the maybe the interactions in the group. So yes, we do realize that there are several things that we could do to, like I said, improve the interaction, and that's probably necessary now because we are getting into a part of the course where the concepts are becoming deeper and it's not so tolerant to missing lectures or missing some part of the lecture. So you're going to have to be that much more tuned into the course at this point, right? So I figured, the one thing that least we could do is have this weekly session where we can interact with you about the tutorial problems. I will certainly schedule a different session, an extra session maybe later this week, maybe on Saturday, wherein we will talk about common questions that you have related to the lectures and all the concepts that we are teaching in the lectures. But this particular session we will try to keep to the tutorial related questions. So you already saw Anand, who is actually handling tutorial this assignment 7, and which is due I think tomorrow, right? I think, yeah. And then you'll also meet Suresh, who is handling the next week's assignment. So he will be able to answer you any questions that you have later on. But I would think that you're probably more interested in figuring out the answers for tutorial 7 at this point. So we will focus on that. So there have been a few questions that we have received from you. Normally I will have all the questions in front of me, so it's easier to answer them. What I will do is I'll just answer some generic questions, and then we will I will hand it off to Anand to give you some answers for the specific questions. Okay, so one question that we got was that of the distributed loss coefficient. So somebody was asking, what is the can we throw some light on the distributed loss coefficient? And maybe I can spend a few minutes talking about that upfront. So we need to move on to this pad here. Can you just call him? To switch to this pad here. Just hold on for a second. We need to switch to this. Okay, so in a gain medium, right? So if we are actually talking about Fabry-Perot cavity, right? So we said R1, R2, and then you have a certain gain medium which has a gain coefficient gamma, but also a loss in terms of internal loss in terms of alpha int. And we had talked about this a couple of weeks ago, where we said we were tracking the gain inside the cavity, which is gamma multiplied by 2L, where L corresponds to the length of the cavity, and that was equal to alpha int multiplied by 2L plus ln of 1 over R1, R2, right? So this is what we had looked at before, and this expression now we said where gamma multiplied by 2L corresponds to the total round trip gain, alpha int multiplied by 2L corresponds to the total integrated loss inside the cavity, and ln of 1 over R1, R2 corresponds to the loss at the mirrors. Now we divided this entire expression by 2L, and then we said this is equal to gamma equals to alpha int plus 1 over 2L ln of 1 over R1, R2, right? Now this expression over here, just trying to look at this color, but okay. So this part here is what we call as the distributed loss coefficient. So why are we saying it's a distributed loss coefficient? Well, if you look at this quantity, the gain coefficient, that's in terms of per meter. Alpha int is also per meter, so this will also have to be per meter. But what are we representing here? This is actually representing R1 and R2, the mirror losses, which is actually a lumped element. So this lumped element, this lumped loss is, we are having to actually represent it in some distributed manner, and so that's why we call it as the distributed loss coefficient. However, it needs to be noted that the distributed loss coefficient does not have a physical connotation. It is just the way we are representing it, so that it can be brought in along with to explain the total losses inside the cavity to get to this particular expression. So hope that clarifies the question related to the distributed loss coefficient. I'm going to have to suspend this for a second because we are finding some problem here with this discussion. So let me just quickly stop the session right here and then handle this issue and come back.
Stop. Still, please.
க்ளோஸ் பண்ணிட்டீங்களா? இல்லை இது மியூட் பண்ணுறீங்களா? இப்போ
வால்யூம் மியூட் பண்ணுமா?
Okay, so I'm back and we are continuing to discuss some of the other questions that I have here. By the way, that explanation about the distributed loss coefficient is probably what we have for some of the other questions also. Maybe we'll deal with that at a later point. Okay, there is one more question as to discuss the effect on when FBG is introduced into the ring laser. So what we are talking about is in a ring laser cavity you have the gain medium. So let's say this is the gain medium. And normally what we said in a free running laser, we will essentially have an isolator here so that it allows unidirectional propagation. There is some coupler here, what we call as a WDM coupler, which allows you to couple the pump. and finally we take the a part of the light using another coupler over here, which is allowing you to take out the output power. Right now, this is actually a free running laser, meaning that this laser can oscillate at any wavelength, any longitudinal mode which satisfies the condition that we have a gain for that longitudinal mode which is at least equal to the loss in the cavity, right? So that's the condition for oscillation of this longitudinal mode. But having said that, if you look at the for example the gain for the erbium doped amplifier, the gain spectrum may look like this. The peak is at 1530 and so on, and it comes down around 1560 nanometers, right, wavelength. And we say, okay, the loss is happening over here. So as the loss changes, the laser oscillation actually changes along with any change in the loss or any change in the gain also. So where the gain meets the loss, that corresponds to the lasing wavelength, right? And this lasing wavelength can potentially be anywhere across the spectrum where the gain is overcoming the loss inside the cavity, right? But there are conditions where you want the oscillation to happen only at a particular wavelength. Let's say you want the oscillation to happen only at this wavelength of 1550 nanometers. Then what we are doing in this case is we are introducing a circulator inside the cavity. A circulator is an element which allows light from port 1 to go to port 2, and any light reflected from port 2 goes to port 3, right? So we introduce this element called a fiber Bragg grating, right, which I have explained during the regular lecture. So we introduce that element so that it provides loss for all other wavelengths. It reflects only at 1550 nanometers, and all other wavelengths will escape the cavity through this. So they will be highly lossy. So only at 1550 you will overcome the loss in the cavity, and so only 1550 nanometer will be oscillating. So that is the effect of introducing the fiber Bragg grating in the ring laser. And related to that, there was some question, I believe.
How the loss changes inside.
How the loss inside the cavity changes is now you need to look at what is the loss in the circulator. That is this pass loss. But that loss we had, I think, asked them to neglect.
Yes, just the FBG of 5.
So the grating has a reflective of 90%.
Yeah, you can just take any random number and get to the qualitative.
Yeah, so if we say this is 90%, now 10% of the light at 1550 is lost in the fiber Bragg grating. So that becomes an extra loss as far as the cavity is concerned, and so that is what we wanted you to take into account while you are calculating the overall loss in the cavity. Okay, so hopefully that answers the question. So then there is a question about ASC power. So what we talk about ASC power is, so whenever this sort of oscillation happens, when you look at the power spectrum as a function of wavelength, we see that you have this large oscillation at 1550 nanometers, but you also have, because of amplified spontaneous emission, you have some light around 1550 nanometer, and this is corresponding to the amplified spontaneous emission. So because of the fact that the spontaneous emission is a random event, the amplified spontaneous emission tends to be with random phase, and even the frequency is not very well defined. It can be any one of these frequencies under the curve here. So because of that fact, the ASC works out to be more of a noise as far as the laser is concerned. In this case, a laser, but in the case of an amplifier, also that ASC becomes a noise in the process. Okay, so hopefully that clarifies the question. If there are other questions you may ask. We did have some disturbance from a couple of people who are having an irrelevant chat, so we just got them muted, I think, so we can carry on with other questions that you may have. So there are some other questions about a book on fiber lasers apart from Saleh. So there are a few books on fiber lasers, nothing that I can pull out from the top of my head. I think there is Rinyev is another book. If you do a Google, you should be able to find it. If you can't find it, send me a message. I will give you some more information. So Manjari is asking about co-pumping and counter-pumping. So in the case that we are talking about here is where because of the presence of the isolator, the light, the signal actually is traveling in this direction, whereas your pump is traveling in the opposite direction. So this particular scheme is what you call as counter pumping scheme. But if you had the WDM over here, let's say if you had the WDM over there and you launch the pump from this side, this would correspond to the co-pumping configuration, because in this case the pump is actually traveling in the same direction as the signal. So that is the difference between co-pumping and counter-pumping. So Arjun has this very nice question about what if we don't have an isolator in ring laser and make it bidirectional. So that is quite possible, Arjun, as you pointed out. If we remove this isolator and if we don't have a circulator also, because the circulator essentially works like an isolator, it's basically a two path isolator. If you don't have a isolator and a circulator, you could have the signal from this direction as well as this direction. So both sides the oscillation can happen, and in that case you have what is called a standing wave pattern. That's similar to the case of a Fabry-Perot cavity, where you can have oscillation in both directions. And what we saw in that case is, you have something like this for a wave that's traveling in one direction, and the other direction it's going like this, right? So you have certain nodes and antinodes inside the cavity. So at these regions the intensity is actually 0. so you don't have much saturation of the gain, whereas at these regions the intensity is high, and because of that we have basically the gain gets saturated, so gain saturation happens. So you have an effect what is called spatial hole burning that is happening, because the spatially the gain is actually getting saturated, right? And so what's wrong with that? Nothing's really wrong with that, except that this picture that I have drawn corresponds to one particular longitudinal mode. So when you have the saturation, it tends to jump to the next longitudinal mode and so on. So it goes basically jumps to the a different longitudinal mode, and then from there it may go to a different longitudinal mode and all that. So effectively what we are saying is, if you consider just this one wavelength, if you zoom into that, you will find that within that wavelength there may be possibility of multiple longitudinal modes, and there will be because of the spatial hole burning, you will have competition between longitudinal modes. So that competition corresponds to some fluctuation in the intensity of the laser, and that might actually give rise to some intensity noise. So if you want to remove spatial hole burning and remove this mode competition, you go for an isolated ring cavity with an isolator, so that you have only that you don't have bidirectional operation, so you don't have like a standing wave pattern that's happening in the cavity, and you won't have this issue with mode competition. So that's the advantage of having just unidirectional operation. So the question then is, which is the best cavity, linear cavity or ring laser cavity? Well, that depends on the application, but in this application, if you want unidirectional operation, you have to go for a ring laser cavity. You cannot do that with a linear cavity. Okay, so hopefully that answers the question. Right, I think there are other questions specifically related to the assignment, so I'm gonna ask the other TAs to step in and answer those questions. Yeah. I've got to go, guys. I have some other appointment. I'll see you guys later in the week, hopefully.
So I think sir has already explained first few questions. For circulator to find the optimum transmissivity, I think there is a formula for that is already in the last video of the laser part 4. I think the title of the video was laser part 4. I think there is a formula for that. Explicitly, you can just look that up. After that we have clarifying the difference between co-pumping and counter-pumping. Sir has already explained that, and in fiber lasers specifically, you have to understand what the co-pumping and counter-pumping does to for a amplifier, and then try to extrapolate that, is that advantage valid for fiber lasers? Because in co-pumping and counter-pumping, basically you had an advantage in counter-pumping because you were you were pushing in the pump from the other end, where the and putting the signal from one end. So what ended up happening was, when we have more signal photons, we need more pump photons where there are more signal photons. So counter pumping kind of decreases the spontaneous emissions, and in turn decreases the noise. So is that logic valid for fiber lasers? That you have to figure that out. And what is the formula to find distributed loss coefficient? I think sir has already written that out explicitly. Then there is one more question. The value of total loss, LEX, is not given. So here LEX is not the value of the total loss. LEX is the value of the losses except for the mirror, basically. Except for the mirror from where you are getting the power out. Everything else comes under LEX. And we have given a photon lifetime in the question. So from there you should be able to calculate what the LEX should be. Because you have already calculated alpha D, the distributed loss coefficient for the coupler. So subtracting that from the total photon lifetime and getting the total distributed loss from the total photon lifetime, you can get to the LEX. And then when you and then when you have to introduce the FBG, you'll have to add, because that is going to introduce a little bit of more loss to LEX. You can just, if you are not able to answer that, question, what was I saying? Yeah. So if the LEX, so when you're introducing the FBJ, that is a qualitative question that I have asked. So if you're not able to answer that qualitatively, you can just assume that it is at 90% reflectivity at the specified frequency, and then incorporate that into LEX, because that's not where you are trying to get the laser output from. So that is going to contribute into decreasing the photon lifetime there. So the next question is the distributed loss same as the loss produced from the mirror too? No, it's not. We don't have mirrors here. In the fiber ring laser, we don't have mirrors here. So I think this is a question from Aishvi Jain. Is this a question from assignment 6? Could you text me back? Because here in the FRR you don't have mirrors, you just have one coupler from where you are getting the laser output from. Okay. Yeah. So question 3, assignment 7, the answer, the powers of 10 to the 28, I think there's a technical problem there. We'll fix it ASAP. The last question, they are not able to write. Is the scientific notation not supported?
Yeah, I know that is some.
He'll check after that. So I think that should be fixed before today. So don't worry. To calculate LEX2L alpha int alpha M1 for circulator, there is no separate losses for mirror 1 and mirror 2. There are no mirrors again. So totally we are considered as alpha D. But while calculating LEX here, there is no internal losses, no separate loss associated with M1. All that information, everything is accounted for in the photon lifetime that I have given you. So you just all the losses, everything is there in the photon lifetime, and then you have to just subtract whatever information that you have. Like you have the total photon lifetime, and after that you have you have the total photon lifetime, and after that you have been given the how much power can you get out of the coupler, right? So you take that, you get the distributed loss coefficient from that coupler, and then you subtract it from the photon lifetime, whatever the loss you get from the photon lifetime, and then you get everything that you want from there. So you don't need explicitly what the internal losses are, what the mirror losses are, because there are no mirrors again. So yeah, I'm answering your question here, Bharati. Are you getting it? Basically, you don't have to have alpha M1 and everything, you just have alpha. Excuse me. Suresh? Do you have assignment 6 questions with you?
No.
I think assignment 6 questions have already been solved. You can check the solutions. I think they're uploaded.
So,
Is the distributed loss same as the loss produced from the mirror too? So the distributed loss, again, sir has already told you, you have the formula for Fabry-Perot cavity, how from mirror losses you can get to the distributed loss. So I think that is covered there. Guys, am I making sense? Like, Bharati, are you there? Did I answer your questions? Please respond. I have, and I hope I have answered. They're not responding, I don't know.
okay, then finish it. I will call. Okay, it's finished.
Wait. SLEX equal to 2L.
So this is L is loss or length?
No, LEX is in the expression that they have, like,
It's a loss or length.
it's the loss. It's the loss except for what you are getting out of the laser cavity, basically. I would recommend you go through the lecture, the last lecture again. Question 3 in assignment 7. Question 3 in assignment 7. Yeah. Population inversion. There is a direct formula. Sir has written explicitly down in, I think, video number 2 or 3. You can go look that up. And about question number 3, assignment 7, I understand that there is some problem in entering the answer. That is going to be fixed today. I hope that answers your question. SLEX to L. Bharati. Okay. Could you be a bit more discreet, Bharati? What are you asking?
You will also get in holidays. You have to work.
Work, sir. So,
Okay, you have to work.
sir, work.
Uh,
Not confirm. Student also that is the
Students and scholars.
staff.
Staff no.
yeah. So, but
Staff also. Much projects.
while deriving optimum transmissivity, sir has given so LEX is supposed to be whatever losses. Yeah. So again, you'll have to think about putting in 2L there. I don't want to solve the question here. But I would tell you that you just have to take how much, what is the length that a photon is traveling inside the cavity. Like what is the round trip length? You can call it something like that. And yeah, alpha int plus alpha m1. So what does that mean? You were getting the power from mirror 2, right? And you were putting all other losses, you were multiplying all other distributed losses with the length there. So you have to do something analogous here. You have to just subtract whatever power you are getting out and then do find the LEX. I don't want to solve it here. You can see through the solutions which would be uploaded tomorrow after a couple of days, I guess. So Ashvi is asking if we need a laser to have its application in bidirection, then is ring laser cavity still better than the linear laser cavity? The applications are very different when you are using a ring laser cavity. But in a sense, if you didn't have any isolators, you would get bidirectional lasing. It would create standing waves, whatever happened there. But in that diagram, I think you had sir did okay. So where is this? I think sir drew anyway. I don't want to do anything here. So we had something like this. This has the entire laser part and pumps and all going around. We had coupler here where we had our pump going in here. And if we didn't have an isolator, then we would be getting our signal could be going this way and both this way, right? So it would also come out of this way, and we could also get it out of this way. So you can get a bidirectional application from the ring laser cavity, but I don't think there are a lot of applications for that. So I think I answered your question. Sorry about my art there. See, mostly ring laser, we can get longer rings, right? So if we can't do very high concentration doping for some reason, like for alpha or something, if we want a if we want our gain medium to be of a way longer length, for example, we can't have a kilometer long linear laser, right? So if you want something like that, you could use something like a fiber ring laser, or most of our diode lasers and everything things are some variant of linear Fabry-Perot lasers. Is that it?
You want to answer more?
I don't know, like they have to tell me something, right? Or should I just go leave?
They will not tell you how they can tell. They have
Okay,
type.
what is...
They have
is
to type.
yeah, but what is the time that we can...
No problem. You can close.
It's done,
Close
right?
up.
Okay, guys.
It will be there and they will keep
Just
asking.
I'll just give them my thing 1 minute to do something else. Something.
Stop it, stop it.
Just stop.
Okay.